Eric.
What?
Hey guys. Picking up where we left off last class, I'm looking at the notes for section 6.2. What we talked about towards the end of last class was what happens if we combine two random values, like x plus y or x minus y. Well, one thing we looked at was the average of the sum is simply the sum of the averages. The new standard deviation, we have to actually take a roundabout way to get there a little bit, and we have to find the new variance, which is the sum of the individual variances, which of course we could square root that to make it into the standard deviation. Even if we are subtracting two random values, okay, the mean is found by subtracting the two means. The standard deviation is found, though, by still adding the two variances and then square rooting. So on these notes, there's a couple of all right, so coming here, we are going to look at random variable x, where x is going to be the weight of an apple. And we are told that apple weights are normally distributed with a mean of 9 and a standard deviation of 1.5 ounces. Now, a bag of apples is going to be created by putting 12 apples in the same bag. So you're going to get an apple, put it in the bag, then another apple, put it in the bag, another apple, put it in the bag, etc., until you get out to that 12th apple. Now, in all of your experience with algebra, you know algebraically that is 12x. Statistically, though, it's not necessarily 12x. Okay? But anywho, here's what we would know. What would be the average weight of a bag? Well, we would expect each apple we get on average to be an average apple. So we'd expect the first apple to be 9 ounces on average, the second apple to be 9 ounces on average, the third, fourth, fifth, sixth, seventh, all the way out to the 12th apple. On average, it'll be 9 ounces each. So the average weight of the bag, I bet every single person in here could get that without needing to listen to me. It'd be 108 ounces on average. The standard deviation for the bag of apples, though, is tough, because what people want to do, the temptation, is just to think it would be 12 times 1.5. But statistically, that's actually not right. Okay, and this is what confuses some people. Okay, because we're adding up 12 individual things, what we have to do is add up the individual variances. So it'd be 1.5 squared plus another 1.5 squared all the way out to that last 1.5 squared. To make it the standard deviation, we'd square root all of that stuff. So literally what we're square rooting is 12 1.5 squareds. If you do that arithmetic, it's 5.2 ounces. Now the question up above says, what's the likelihood that the bag of apples will weigh less than 100 ounces? So what's the probability the total weight of the bag will be less than 100 ounces? Well, what's great is, since each apple is normally distributed, that means the bags will be normally distributed in weight. We now have the average of 108. We have the standard deviation of 5.2. What that allows us to then do is do a pretty straightforward normal calculation after we've done all the complicated stuff above. So we have a normal curve centered on 108. What's the likelihood the bag will weigh less than 100? You'd have to z-score 100 by subtracting 108 and dividing by that standard deviation of 5.2. That's negative 1.54. You look that up on the table. There's formula packets on the front table, by the way, you can grab for the normal curve table, and boom, about a 6.2% chance we'd get a bag that weighs less than 100 ounces. Right? Now behind it says, if you have a random variable x, and x is known to be normally distributed, and it has a particular mean and a particular standard deviation. You have another random value y that comes from a distribution that's known to be normal with a particular mean and a particular standard deviation. And you are then going to either take a randomly generated value of x and a randomly generated value of y and be interested in the sum of those two things, where last class this might have been how long you wait for food and how long you wait in the soda line. Or you can find the difference between the two random values. Maybe this is a randomly generated height of a man, randomly generated height of a woman, and you want to find out how much taller the man is or what the difference in the heights are. Well, if x is normal, and if y is normal, and if the two values x and y are generated independently of each other, then a couple of wonderful conclusions. X plus y, therefore, would also be normally distributed. X minus y would also be normally distributed. Yay! It's like earth-shattering stuff, isn't it? Okay, so we'll apply that rule to. Next example is on the last page, or the last example on your notes is similar. This one's actually, I think, a little bit easier because we only have two random variables here. Here we have men's heights are part of a random variable distribution where the heights of men are known to be normal with a mean of 70 and a standard deviation of 3.5. W is going to represent the heights of women. It's given that the heights of women are also part of a normal distribution with a mean of 65 and a standard deviation of 3. Okay, I've created a situation here where we have arranged marriages where the man and women are picked via a lottery. And so married couples are created by randomly selecting a man and a woman from the population. What's the likelihood the woman would be taller than the man? So if you look at the value of m minus w, that would be the difference in heights. Okay. Now, if the woman is taller, that means m minus w would be taking a negative value. So what we're looking for is the probability that m minus w would take a value less than 0. Now, the only way we can answer this probability question is if we have a very, very special case. Okay, and that would be 1. Is the first random variable m normal? Okay, check. Second thing, is the second random variable w normal? Okay, check. Third, are the two values independent of each other? Check. And that's why I wanted these marriages to be arranged to be a lottery so the value of m and w are independent of each other. So now we have an important situation here. The random variable m minus w, therefore, is also going to be part of a normal distribution. Okay, the average difference in heights, I think logically you guys would all know, would be 70 minus 65, or 5 inches on average. Now the standard deviation of the differences was a little more challenging to figure out. We talked about this last class though. It would be the square root of the sum of the two variances, which is basically 4.6 inches. So now what we've got is a relatively straightforward normal curve problem after we've done all of that previous stuff. So the difference in heights would be an average of 5. If the woman is taller than the man, that means the value of m minus w would be less than 0, or negative. Okay, so we'd z-score that value by subtracting 5 and dividing by standard deviation. Okay, that z-score, I believe, is negative 1.09. Okay, the formula packets from the front table will have the normal curve table in it. You look that up. The area is 0.1379 inside of there. So there's about a 13.79% chance that we'd randomly pick a couple where the woman would end up being taller. Okay? So hopefully that explanation makes sense and you can handle the problems on the study guide and out of the book for homework.